This is part 3 of the KBYP Midas Touch video on the Eimac care and feeding and mighty tube computer. And I've decided on this load line. And interestingly enough, by careful measurement, the end of this line coincides exactly with 1.2 amp. Exactly. Which is Eimac's assumption. So 3 points agreeing pretty much guarantees that's going to be accurate. This is an extremely poor document. The grid lines, the square grid lines are very poor. And it's extremely difficult to interpolate between these black lines and get a current that's anywhere near accurate. The way to solve that is with a pair of calipers. Get a pair of cheap dial calipers for 10 or 20 bucks. But put the calipers on the two dark lines, which correspond in this case with 1 amp and 1.4 amp, and measure the distance. 1.2 amp is exactly halfway in between those lines which are 0.750 inches apart. So to divide that current in two, divide that 0.75 inch figure in half down to 0.35 inch and put that on the 1 amp line and mark a point, and that's it. And that coincides right with the end of that line as accurately as I can draw it. And that can be scaled for any current in between any of these sets of lines, but realize that the measurement has to be made along these voltage lines. It can't be off this way. It has to be between the two black lines along one of the voltage lines. Then just do simple proportion to calculate the distance and use the calipers to measure and mark that out. The mighty tube computer process is to take the calipers and realize I'm working unrehearsed here. None of this is rehearsed. This is all off the top of my head. Measuring the length of that line and transferring that to the tube computer thingy from there to there, which came from that. Print that page out, mark that line, the length of the load line, and cut the rest of this paper off. And realize that there's a gross mistake in editing this document where they say, come on, give me focus. In step 4, place the computer on the curve sheet with guidelines parallel to the operating line. Make the OG line go through the point marked in step number 2. If you read the original care and feeding document, it says make it go through OA, not OG. So they have thoroughly screwed this up with poor editing. So take this bit that's been cut off and line up A with the top of the line and G with the bottom. It's convenient to mark A, B, C, D, E, F on these red lines coming off radially. But go along to the end of each line, and I make a hash mark here for each of these. And those can be marked A, B, C, D, E, F, G. Then with the calipers, go along and measure. Point G is an endpoint, don't need to do anything there. Point F falls right on the 0.2 amp line. Point E is about here. We know what that is. That's 454 milliamps. We calculated that. This mark here is partway between the 1 and 1.4 amp. So we can measure that distance here and proportion that out to see how much that distance is. Take that proportion to the whole span and multiply that by the difference between 1 and 1.4 amp, which is 0.4, and then add that amount from here, actually from here to here, which would be about maybe about a fifth. That'll represent some current like, I don't know, some 50 or 100 milliamps. And then go add that to the 1 amp figure, and that will give the exact current represented for that point, without trying to read these little squares and interpolate, because that's next to impossible. That's all well and good for the plate line, and with 3 points exactly coinciding, we're all but guaranteed that's a correct line. And we see the top of that line goes up basically to the edge of that distortion region, but my guess is, since they're telling us minimum distortion, that doesn't actually go into it. So realize these are curves at different current steps, every 100 or 200 or 400 milliamps. Lots of lines missing off here. So even our best measurements and guessing doesn't prove that that's 1.2 amp exactly, but it's going to be pretty close. Where this becomes much more difficult is this max signal driving power. That is not the power into the tube grid, it will burn up. Max signal driving power implies from an exciter. And if we get the grid dissipation off the computer, we'll find out it's not 45 watts. So why does it say maximum signal driving power? Denoting footnote 1 approximate value. Well, it turns out that through the magic formula, 8 times power times resistance, multiply that together, take the square root, that gives us a peak-to-peak voltage of a signal from a transmitter, for example. The math is thus: for a 50 ohm transmitter and 50 ohm load, 45 watts times 8, 8 times 45 times 50, take the square root of that, so it's 134 volts peak to peak. That's that. From the exciter, we're only using half of that. We're using that part to drive the amplifier. Half of that waveform is 67 volts peak. If we notice over here, the top of this line at 1.2 amp coincides with each minor division being 2.5 volts. Coincides with 90 volts drive. And the 50 ohm 100 watt transmitter can only generate a voltage swing up that graph of minus 67 volts, which is down there at 67. The 50 ohm transmitter, 100 watts, can only swing 67 volts half cycle. It cannot swing far enough to drive that tube to full plate current. So what's going to happen is this load line is going to fall to the left, or be shortened, whatever it's going to do, to coincide with this 67 volt line. So power output is going to drop significantly. That's a good bit of that distance. Notice the driving impedance is 112 ohms. There's 7.1 picofarad grid to cathode, which at 80 meters is 6 k ohms in an open circuit. So that means the tube input at 80 meters is basically just 112 ohms. When we redo the math, 8 times 45 watts times 112 ohms, we get 200 volts peak to peak. Half that for peak at the 45 watts on a data sheet is magically enough to drive the grid at 1.2 amp, just a little bit to spare. So that proves that a 50 ohm transmitter, 100 watts, cannot drive this amplifier. The power output will be down. Maybe less distortion, I don't know. But it will not drive it to full power for this case, which is supposed to be 445 watts useful output power. The trick is to then know how to fix that. And that's a lot more complicated than just making this line. Also realize that that's for safety. It's extremely important to do these kind of things up ahead of time and try to get these things right. Because if there aren't, that implies that we might be tempted to get inside this working high voltage amplifier to try to change or tweak things. That's dangerous. One wrong move, one forgetting to let the plate discharge, and you're dead. I intend to make this a no-tune output, which means there'll be no variable capacitors, no variable inductor. Will be fixed for each band. So there's no room for mistakes here. It's got to be right or it simply will not work, because there will be no knobs to twiddle. As to metering, amplifier units usually have metering put in them. I'll have a meter in mine, but it's only going to measure 5-volt filament, 12-volt control and fan, and plate voltage, because there's no point in measuring anything else. What's the point? Yes, so the grid current can be measured. There's no reason to. The amplification factor and or transconductance are a function of plate voltage and grid drive. There's nothing else. Give the filament plenty of power and forget about it. But if the plate voltage is right, just increase the drive power from a little lower figure until the plate is the correct resistance to match the output network, and there should be a peak in power, and call it good. If the tube is drawing more current than it should, that means something's broken, and it ain't the tube, unless the tube's shorted. But if the tube is weak or wears, the current will go down, not up, and that's going away from a danger zone of higher dissipation. Higher dissipation will occur with maybe excess drive, with higher plate voltage, or a mismatch in the output network. But get the output network right in the first place, and that's not a problem. So metering is rather pointless. So this evidences that the maximum signal driving power is the measured power output from an exciter, but only half of that is used by the amplifier, so at most half of 45, which is 22.5 watts. If you look in the care and feeding, I think it's section 5, they show that the grid input is a matter of 5 or 6 different things, not just energy consumed by the grid. There's also, if there's a resonant network, losses in that, and several other factors that mean that this grid input to this tube is only going to be a few watts. So a 100-watt transmitter has far more than enough power to supply, but it cannot give enough voltage swing to satisfy the amplifier no matter how high the power is turned. Because without some kind of matching, the 50-ohm transmitter will be looking at 112 ohms, which is about a 2.1 SWR. Back in the old days, that was bad enough. Throw a resonant circuit on it, peaks, and try to get enough swing to satisfy the input of the tube. But nowadays, with these modern solid-state transmitters, they tend to have computers, and they can sense an SWR and fold the power back. So couple that 50-ohm solid-state computerized transmitter into this, like the ASU857 control head there, into this, and the computer in that rig is not going to like it. It's going to scale the power back. When it does, the voltage will go down till it's satisfied it's operating in a safe area. And I don't know, it might get 25 or 30 volt swing, peak swing out of it. I don't know what it'll be, but it's not going to like it. So impedance matching is required to make a modern solid-state transmitter drive this fully. And with a few remaining seconds within YouTube's 15-minute limit for cheapskates like me, always a word on safety. This here is the he's dead Jim range if you touch that power supply. Down here will knock you on your ass. This is a Drake TR3 and 4. I've touched that. Don't. It can put you in a pine box. The limits for exposure for voltage in the U.S. under OSHA, occupational, is 60 volts. Anything above that takes precaution. 10 milliamps will kill. Voltage doesn't kill, current does, but voltage can help arc through the outer, dry, more insulating layers of skin and get into the tissue inside. And if current's applied internally, according to the Broadcast Engineer's Handbook, then only on the order of tens to hundreds of microamps is needed to kill. So be extremely careful, because this is dangerous territory. KBYP.